published by H. Gong and G.P. Norden, who Norden is the same guy that we saw his TED Talk last week on microfabrication using 3D printers. And the paper is about a high-density 3D microfluidic valves, pumps, and multiplexers. I should say that the TED Talk we saw last week was in 2018, and this paper was published in 2016. So they did do more research after this publication, which I will briefly mention towards the end, but the majority is going to be about the content of this paper. So I'm going to go over the background, like why benefits of 3D printing, and then I'm going to talk about what to expect from the paper and the rest of the presentation. And then I'm going to go over the experiment and then talk about the results and discussions they obtained. And then I'm going to summarize everything and then talk about what other research they did post 2016. And then we can go into a Q&A kind of time. So in the background, I'm going to talk about the benefits of 3D printing and why 3D printing. So 3D printing is actually, it's supposed to be the new revolution of microfluidic. Like in the 1990s, there was this change from glass and silicon to PDMS. They expect 3D printing to be the same thing during these times. So the benefits is that you don't need a clean room with 3D print, right? So that saves a lot of money. It saves the operation of a clean room. It also saves the time it needs to develop a clean room. It also leads to this rapid fabrication iteration process that includes designing the product, fabricating the device, then testing it, and then readjusting the design. And all of this can be done in one day. According to Norden in his talk last week, when we were in TED Talk that we watched last week, he mentions that a clean room, that's manufacturing, the micro manufacturing of a microfluidic device can take minimum weeks and up to months in a clean room. The use of 3D printing can also lead for non-specialists to use in other fields, in various other fields. Because if you need a clean room, you need specialists for that. You need people to know how to use micro machining, micro lasering, whatever is needed to produce the fabricated device. With a 3D printer, you need the printer to do the work. So you just get the CAD model, turn it into an STL file, and then you have your piece. Which also leads to the fact that you can 3D print complex devices in one go. With clean rooms, you can't do that. Like if anybody manufactures something before, you have to do it piece by piece. In 3D printing, you can do it as one single piece. With all these benefits, there's still some cons with it, and it's that traditional commercial 3D printers, they cannot fabricate those like small voids that are found in the bulk material that we can see in microfluidic devices. So most traditional commercial printers cannot be used. And if one does use a traditional commercial 3D printer, it has to have stereolithographic technology, which requires the use of a liquid resin. So you can't just go and use those regular filaments like PLA or like PLA, because you require a liquid resin, which you can either buy or you can most of the times actually fabricate it in the lab before printing. So the purpose of this experiment is to show that 3D printed devices with integrated valves and pumps can be developed. You don't really need a clean room. And they demonstrated how to use a DLA SLA 3D printer with customized resin formulation, which include a thermal initiator, which dramatically improves the valve actuation, which I will go further on. They also tested the maximum back pressure, which is the pressure needed for the pump to work, and then the maximum flow rate in pumps. And then they took these valves and valve-like displacement chambers and made a 3-to-2 multiplexer that works as a mixer. So the experiment part of the paper can be divided into 3 parts. You can divide it into what was the materials used for the resin, or what 3D printer was used, and the specs of the 3D printer, and then the device fabrication itself, which I think is the most important part. So briefly, the materials used in the customized resin was monomer, a photoinitiator, and an absorber, and then a thermal initiator for durability. So for a monomer, they used which makes up the most of the resin. They use a polyethylene glycol, which has excellent water stability. That when the part is fabricated, there's no swelling and no degradation in strength. Zirdan 1, which is this red substance over here, was used as a photoinitiator. It's only 0.4%, and then 1% of the Agracure 819. And then a thermal initiator is only 0.01%, but it dramatically increased the actuation of the valve, and most of the resin is actually bagged up. So this is what makes up the resin, which was then placed in the 3D printer. You can see here. For this paper, they actually use a customizable. They used a traditional 3D printer that's found that you can buy. But after this publication in 2017, 2018, they customized their own 3D printer. So for this printer, it's an Asiga Pico Plus 27 DLP SLA, which has a LED peak wavelength of 12 nanometer with an in-plane resolution of 20 or 27 micrometer. What you really need to know about this printer is that they used it the build layer was about 10 micrometers. So each layer was built at 10 micrometer. So in this picture here, you can see the resin. So this is the liquid resin that you can use as a sort of filament to make the 3D printer. They had to use a glass slide here. I don't know if you can see it, because of how highly absorbent the resin is. So typically, I don't know if you guys ever 3D printed before or not. Before you print your piece, there's a first layer that's done by the 3D printer, and then the piece is printed. For this case, because of how highly absorbent the resin is, it will take ages for the piece to dry, for the first layer to dry out on the build table of the 3D printer. So they remove that by adding this glass slide, which eliminates the need for a first layer. And also the glass slide is transparent, so you can actually see the process of the build layer of the building. For the device fabrication, so the most important thing is the valve, because everything else is like valve-like, or the pump is made out of 2 valves and a displacement chamber that looks like a valve. So once the valve was made, everything else is similar to it. So let's understand the valve. The valve is comprised of a control chamber, this red circle here, of cylinder, I should say. You have the fluid chamber, the blue one here, and then the membrane, which is right on top of the fluid chamber. Then you have these channels over here. You have the inlet channel, the outlet channel. This is where the fluid comes in and then comes out. Then you have the channel here, which is connected to an external pressure source. So when pressure is applied, the membrane is pushed downwards, which on the fluid chamber, which close the valve, so there's no fluid flow. And then you have a flushing channel, which is used to remove the unpolymerized resin after the 3D printing. This is the CAD of a 3D printed valve. So this whole structure was actually 10% of the original structures they developed in 2015. So it's much smaller in size and much lighter. The printer, the minimum diameter of the valve of the chambers was only 1.08 millimeter, because again, it's a commercial 3D printer. When they customized their own printer, they went down to 150 micrometer instead of 1.08 millimeter. So the valve can be either open or closed, right? Open valve allows the fluid to flow in from the inlet and then out of the outlet. There's no pressure being applied in the open valve. When pressure is applied, right, in a closed valve, this is the control pressure. When pressure is applied, the membrane is pushed downwards towards the fluid chamber, which closes the flow between the inlet and the outlet. So there's no fluid flow happening. So they control that by applying pressure. This is the same process as this, the same picture really. This is just using a photomicrograph. So you can see with better pixels, and you can see in the open valve, there's no membrane. But then in the closed valve, you can see the membrane being pushed down against the inlet and the outlet channels. So after they fabricated the device, they had to go through certain processes, right? Including removing the unpolymerized resin using a vacuum from the flushing channel I talked about. And then they placed the channel, the structure in the IPA for 2 or 3 minutes, which activates thermal initiator. And then the thermal initiator is also more activated during the baking process, which they found is to be 30 minutes at 80 degrees Celsius. They found that 30 minutes to be the most optimal time for the best robust membrane, for the best fabrication yield, and then for the best short time. So they tested different times and they found that 30 minutes was the best. They had to bake the structure because UV exposure was ineffective at curing. They tested the UV exposure, but because of how high absorbent the resin is, so the piece is actually very high absorbent, it really took hours for 1 millimeter of the whole structure to be cured. So they just went with baking instead. And then after that, they included microbore PTFE tubes inside the channels, and they used epoxy for that. So it's actually kind of glued the tubing inside. The whole process took about 4 hours, which is great. Then this is the main key factor of using 3D printer. Instead of taking weeks to fabricate the material, it only took 4 hours. So less than 1 hour for 3D printing, 5 to 7 minutes of flushing and polymerized resin, 30 minutes to bake, and then 2 hours to apply the epoxy and allow for full curing. They did say that if you use like a 5-minute curing epoxy, it will only take 2 hours, but they advised against that because they tested it with one valve and the valve did not reach. I think it stopped after like 1,000 actuation. So in the results section, it's divided into 3 parts. I'm gonna talk about the results of the valve itself by itself, then the results of the pump, which includes, this is the pump, 2 valves and a valve-like displacement chamber. And then we're gonna talk about the multiplexer and the mixing of the multiplexer, the 2 different techniques used. So this is the valve, right? So we talked about this, right? This is a closed valve, the pressure is applied, membrane is deflected downwards, no fluid flow. To calculate how much pressure is needed to deflect the membrane, they use the applied control pressure, right? This P over here, minus the flow of the fluid, the pressure of the fluid, which is moving in the opposite direction. And you just subtract it and you get this pressure here, which is how much you need to deflect the membrane. In another paper, I think in 2015, they did this test in which they looked at the fluid chamber height and the difference and how it affects the pressure. And it's obvious that with increasing thickness membrane and with increase in height in chamber height, you're gonna need more pressure or more stress to push down the membrane. That's common sense. But they did this test and they found that when you increase the height from 50 to 80 micrometer, the pressure doubles. So for this experiment, they did a constant 60 micrometer constant fluid chamber height, and they found this is the best for fabrication yield. So they tested different ones in another paper, but for this one, they just used the 60 micrometer constant value. They developed 54 valves, and out of the 54, 53 reached 1,000 actuation, and 1 reached 1 million. They only tested 1 for 1 million because of time, because it's time consuming, but they're assuming that the other 52 will reach the 1 million. The one that did fail, it reached 1,000, and they think that's because during the building process, during the 3D building process, there was a leak to the voids, and they think that could be avoided if they increase the pixel from 4 to 6 of the between the voids when 3D printing. The pump, like I said, is made out of 2 valves, right? You have V1, which is your inlet valve. You have V2, which is your outlet valve. And then you have this valve-like displacement chamber, which really just the valve that's backwards. And the only difference between them is the channels here, where the pressure is applied, is at the edge of the displacement chamber. And then for the valves, it's in the middle. By placing this in the edge, it allows it avoids the displacement chamber to control if the fluid moves or not. So you don't want the displacement chamber to control that. You only want the valves to be, if they're closed or open, to control the fluid flow. This is the isometric CAD design. Over here, you have the side view. You can see the valve 1, valve 2. You have the displacement chamber, which is placed in between them. And this is the back view. C1, C2, and C3 are channels connecting to an external pressure. And so that's how you control if the membrane deflects downwards or not. The pressure they found to be ideal for applied control pressure was 9 psi, which I will talk about in the results section, but that was what they used for the experiment throughout. You have an inlet channel, which is connected, and an outlet channels, which are connected to an off-chip fluid source and sink. And this is what a pump looks like. So let's talk about some of the phase of the pump, like how does the pump work, right? So the pump works in a 5-phase cycle from T0, which is right before like time equals 0, all the way to T4. At T0, everything's closed, right? V1's closed, V2 is closed, DC is closed. But then the pressure is now at T0, pressure is being applied to the displacement chamber, which opens up. And when you apply this pressure, the membrane goes back to equilibrium. So when membrane goes back to equilibrium, V1 opens. So when V1 opens, there's fluid going through V1 to DC. So at time 2, the membrane deflects again at the inlet valve, which closes valve 1. So all the fluid right now is being in the displacement chamber. At time T, valve 2 opens. So in this phase over here, there's an preparation of fluid being removed from the displacement chamber to the outlet channel, which happens at time 4. So now the fluid is being removed out of the outlet channel, and this is a cycle that repeats over and over again. The cycle is very fast. It just dividing it into sequence so you can see what happens. So other than the phase cycle, so this is what the actual results were. So they tested maximum flow rate, Qmax, which happened with this there's zero back pressure. So back pressure is defined as the pressure a pump works against for that fluid to flow. So when there's no back pressure, there's maximum flow rate. So they tested this for two different conditions. You have condition one with a vacuum and one without a vacuum. The vacuum, I think it was 10 psi, if I'm not mistaken. I don't have it here, but I'm pretty sure it's 10 psi that they used. It just means that there's a vacuum pushing against the membrane to push it back into equilibrium, so it's no longer unaffected. The no vacuum is the regular control group. It just means that the only restoration force of the membrane is the strain, is the elastic strain. So just mechanics materials, right? You pull something, there's a force. You pull it. Once you remove that force, if it's still in the elastic region, it bounces back to its original length or height. So this is the case with no vacuum. With the vacuum, there's an additional psi. There's another pressure pushing against it to return it faster. And you can see that at the phase interval 15 milliseconds over here, there's a maximum flow rate of 40 microliter per minute. And that as you go down, as you increase the time, the flow rate decreases. And you can also see that after this 15 milliseconds, the flow rate with the vacuum is almost double that without the vacuum. Similarly, when you look at the displayed fluid volume is basically, which occurs at phase 3 to 4 in this cycle. Let me go back here. So it occurs in this process. This means how much volume is being removed from the displacement chamber to the outlet valve. So in this case, with the no vacuum, there's almost double the volume being removed than without the vacuum, sorry. And then they also looked at the back pressure. So the back pressure, again, as I said, is just how much pressure the pump works against for that fluid to flow. In this case, it just said 3 control pressures at 6, at 9, and at 11. And then they did like a line intercept kind of thing, like a fit line. And they found that the x-intercept is around 4.5 psi. It just means that anywhere after 4.5, that's when the pump can work and can work against the back pressure. So it can flow, the fluid can flow. So they end up going with 9 psi, as I mentioned earlier. So that was the constant pressure, control pressure used. And around that, it gives you a back pressure of around 4. If you use 11, it's a more back pressure of around 7, I would say, 7.5. But they end up using just 9. They also looked at the flow rate as a function of the height. And you can see that the flow rate decreased as the chamber, as the outlet height, increased. But it's not really that big of a change. So the results were, there's a slow trend, but it's not large differences. So let's talk about the multiplexer. The multiplexer, it looks very complicated if you look at it over here, but I think the scheme diagram really makes it more visible. Like you can see it on a 2D sketch kind of thing. You have 3 inlets, right? You have V1, 3 inlet valves. You have V1, V2, V3 that are connected with the displacement chamber in the middle to 2 outlet valves, V4 and V5, right? They use 3 different kind of fluid: the buffer, the red, which is just red dye with water, diluted with water, and black, again, black dye diluted with water. And you can see here, this is the more complicated 3D printed device, CAD. It looks very complicated if you look at it here, but it's basically the same structure. The only thing I should tell you to look at over here is that V1, V2, and V3 are placed slightly higher than V4 and V5 and the displacement chamber. They did this, so I think it's 15 centimeters higher, just because they want to see, they want to let gravity do the work to enable the fluid flow, as will happen later on. And over here, you just have, this is a visualization of the buffer, the red and the black dye going in at different inlet valves, different outlet valves. In this diagram scheme, I would say, this is just different combinations they did to test, right? So if you close 2 inlet valves and close 1 outlet valve, you can have the flow happening from one inlet valve to the other outlet valve. So this is it. This is red dye or red fluid going into outlet 1. Here you have black being pumped out of outlet 2. Here you have buffer being pumped out of outlet 2. Here's buffer out of outlet 1, red dye out of outlet 2, the black dye out of outlet 1. So again, this is just a combination we think you can do without mixing it. So you can use this as a pump without mixing anything. But the whole point of using a multiplexer is to mix the fluids, right? So they did do that. They mixed the fluid, 2 different mixes. So mixer 1 and mixer 2. This is for mixer 1. You can see this is the red dye and the black dye being pumped at the same time. So both valve 2 and valve 3 are open at the same time and coming out of outlet 2. you can see here that this is going to this displacement chamber, and you can see here that they're not really mixing. So this is mixer 1. So this is what they only have one inlet valve per fluid, which you can see here. So here, R1 is the inlet valve, is the one inlet for the red, and then B1 is one inlet for for the black fluid. For the mixer 2, which they found better results, as I will show, they used 2 different inlets, R1 and R2, and then B1 and B2 instead of just one. And that gave much better results. So this is the same phase cycle almost. This is with using the multiplexer, so with mixing. So instead of having only one valve open, you have 2. So V2, which red, and V3, which is black fluid, and then out the outlet 2. So time 0, everything's closed. Time 1, you have V2, V3, which is the inlet valves, and then the displacement chamber open. All right, so fluid is flowing in. Time 2, fluid is in the displacement chamber, everything else closed. Time 3, the outlet valve is open, in preparation for the fluid to flow out. And then T4 is where the fluid is all out of the valve. So this is mixer 1. This is the results of when they only had one inlet per fluid. You had the start of the cycle. So this is T0, right? So all the valves are closed. Then T1, you have valve 1, valve 2 open. Displacement chamber is also open. Here, you have the fluid all over here. You can see it here, and you can still see there's no mixing. Like you can see some of the red and some of the black. Still, over here, this is time 3. You can see this red streak, which is even more noticeable. There's a little bit more mixing than at this time. That's only because of diffusion. It's not really because the fluid is mixing. And then you can still, at the results, which is time 5, which is back to the start of the cycle, you can see this red streak and the black and the black fluid. They're not really mixing. So when they increase the inlet, it's mixer 2, when they increase the inlet from 1 to 2 per fluid, so you have 2 inlets for the red and then 2 for the black, it's the same process. But what you can see is that they're really mixed up now. I mean, you can see a little bit of streaks, but it's not as much. So it's more, so they theorize that the more inlets you have per fluid, the more mixing is going to happen in the multiplexer. So in conclusion, let's just go over what we talked about. We talked about the potential of 3D printing. We talked about how thermal initiator plus a post-printing bake dramatically improves durability. We talked about how 53 of the 54 valves surpassed 10,000 actuations, with one reaching 1 million. We talked about how the valves were used to make pumps in which maximum back pressure and maximum flow rate were tested. We talked about how the maximum flow rate was 40 micrometer per minute. We also talked about the mixing, using multiplexers as mixers, and how using more than one inlet per fluid dramatically increased the mixing process. And then we talked about the most important thing, I should just iterate again, is that the whole thing took 1 day to test, to fabricate, to test, and to redesign instead of taking weeks. So I'm going to talk about, so this is 2016, whatever I talked about was all in 2016. So what happened after that? This is them after 2016. So in 2016, they used the Asiga printer, and the valve, the smallest valve diameter was 1.08 millimeter. 2017, they customized their own 3D printer. They went down to 300 micrometer. In 2018, another customized printer went down to 150 micrometer. Right, so this is the 3D printer at that time at 300 micrometer scale. This is taken from the TED Talk mostly, and a little bit of one of their papers. And this is the new multiplexer, which includes a lot more valves, a lot more inlets, which again, as to theorize, that will lead to better mixing. And that's about it. Any questions?
Very nice. Thank you, Dina. Any questions from the audience first?
I have a question.